Assalamu alaikum students. Today we are going to learn about statistics and sampling distributions. Before we go into the details of statistics and sampling distributions, we need to know some important concepts and some definitions which will lead us toward towards statistic and sampling distribution. First of them is statistical inference. Now actually we are moving towards inferential statistic. In inferential statistics we make some inferences or conclusions or predictions about a population by making some statistical measurements by using statistical procedures on the samples that we collect from the data. And statistical inference, here it can be defined as that statistical inference is about drawing conclusions or making predictions about a population based on the sample data selected from that population. It means that we actually want to know about the population, right? So we want to know something about population, but we cannot collect measurements, so we cannot measure every item or everything in the population, right? The population can be for example in a manufacturing industry or in a manufacturing process, all the products which are being manufacturing come under population. Okay, we cannot make measurements on all of them. Or if we talk about the human population and we want to know something about country's whole population, we cannot collect data from everyone in that population. So to make our measurements or to make our job easier, we collect samples from the whole population. Samples mean that we select some of the items from the population, and we through some statistical procedures we collect data of interest, means the measurements that we are interested in we make only on the samples which are collected from the population. We call that sample data, and on the basis of this sample data we draw conclusions about the population and make predictions about this population. Okay, this is called as statistical inference. So in simple words we can say that from a whole large population we select some samples, we make measurements that we are interested in, and then we generalize for the whole population. Okay, so when we want to collect samples, one of the very important thing is random sampling. Sampling is actually the procedure of collecting samples or selecting samples. So the random sampling is a type of sampling in which a sample is randomly selected from the population without any bias. So by definition, a method of sample selection in which all the samples have equal chance or equal probability of being selected is called as random sampling. Okay, do you understand? This means there is no certain bias that will lead us towards the selection of a specific sample, so they are totally random. So there are two types of sampling here: sampling with replacement and sampling without replacement. In sampling with replacement, when we select a sample from the population, we refill the population with an identical observation that we have already with an identical item that we have already selected from that population as a part of the sample. Okay, it means that the population does not miss anything. Once we have selected a sample, we refill it or replace the selected sample with an identical one in the population. So in this method of sample selection, each time a sample unit, or we call it observation, is selected from the population, it is replaced with an identical observation in the population. Means, for example, if we have a jar of different colored balls, okay, and we want to select a sample from that jar. So for example, if that jar has three colors: blue color, yellow color, and green color, and we select two blue colored balls from there and one yellow colored ball from the jar. So we collect that, we take them out from the jar, but we refill the jar with the same two blue and one yellow one. So we again add those in the jar, the ones that we had already selected. It means that when they are put back in the jar, we can select them again. So there are multiple, we can select the same sample multiple times. Okay, I hope you understand this. And in the sample without replacement, the procedure, each sample in the population has only one chance of selection. So it can be, means in this type of sampling, means sampling without replacement, each sample unit can be selected only once. Okay, it is different from the sampling with replacement. So in sampling with replacement, one observation can be selected multiple times. Means if there are yellow balls and the blue balls and the green balls, and we select one yellow ball, we take it out from the jar, we refill jar with another identical yellow ball, and that yellow ball has another, means we can select that again, right? So if we take it out and we will refill the jar with another yellow ball, so we can keep on selecting that sample, right? So one observation has multiple chances of selection in sampling with replacement, because we keep on replacing the one that we have already selected, right? But with sampling without replacement, once we have selected a ball and we take it out from the jar, we are not refilling the jar with an identical observation back again. So one sample can be selected, or one sample unit can be selected only once in the sampling procedure. Okay, so a sample will be considered random when it is drawn from an infinite population. Infinite population is the one in which we have uncountable items, means we cannot count the number of items in that population. It is so large. Okay, so by definition, this population will not feel any deficiency after we have selected some samples from it. Okay, so if the sample is drawn from an infinite population, we will consider that sample a random sample. Or if the sample is drawn from a finite population, means it has some boundaries, or a countable number of items in that population, like in general we consider n, capital N, as the number of items in the population. So if the population is drawn from a if the sample is drawn from a finite population but with a replacement, sampling with replacement procedure, so it essentially becomes like an infinite population, because we keep on adding the sample observations back again into the jar, and it does not find any deficiency. We do not see any deficiency in the population and the samples. We keep on selecting samples, and the samples are still there to be selected again. So the sample will be considered when it is drawn from infinite population, or when it is drawn from finite population but with replacement, or when a sample of n observations, small n represent the number of items or number of observations in a sample. Like if you remember previously, we saw that x1, x2, x3, x4 until xn are the number of observation in a sample x. Okay, so you will further see some examples, and you will have a better idea about this. So if a sample of small n number of observations drawn from a finite population of capital N items, so the number of items in a population are represented with capital N, and the number of items or number of observations in the sample are represented with small n. Okay, then if each of n, these are the combinations that we can make. So from capital N, small n is the number, means the number of items or number of observations in the sample. So from this combination, if all the samples have equal probability of being selected, then the collected sample will be considered as a random sample. Random samples have very high respect in statistic because they are collected without any bias. Okay, so there are three conditions under which we can consider a random sample. First, if it is drawn from an infinite population. Second, if it is drawn from a finite population but through the procedure of sampling with replacement, or if the sample is collected from a finite population but sample of size n and the population of size capital N. In this, all the samples of size n has equal probability of being selected, then it is called as then it will be considered as a random sample. This one represents actually the all possible combinations of the sample of size n in the population of size capital N. So if all of those combinations of the observations in a sample can have equal probability or equal chances of being selected, then we call that sample as a random sample. Okay. Parameter is a characteristic of population. Okay, for example, population mean, it is represented as mu, and the population variance, which is represented with sigma square. So population is a parameter that describes a characteristic of a population. Okay, so parameter is related with population. Then there is statistic. Statistic is different from the branch of science statistic. Okay, the statistic is actually the characteristic of a sample. Just like parameter is the characteristic of population, statistic is the characteristic of a sample. Remember, sample is a subset of population because we select it from the population. Okay, so statistic is a characteristic of a sample which is drawn from a population. For example, sample mean, which is represented with x with a bar on the top. Okay, and the sample variance, which is represented with s square. Okay, and then sample statistics can be used to estimate population parameters in inferential statistic, because as you know that we do not measure sample parameters, right? Because in order to we do not measure population parameters, because in order to measure this we need measurement from whole population, all the observations in all the items in the population, but it is really a hard job to do, or nearly impossible to do. So what we do is we collect sample and we make measurements on it. For example, if we want to find out the population mean, so instead of population mean we will find out sample mean, and then we will estimate about the population mean. And if you want to find out population variance, we will calculate, or we will measure sample variance represented with s square, and then we will estimate the population variance. Okay, now it will lead us to the estimation and how statistics can, or how the statistics for different of the means, how different statistics can be used to estimate population parameters. So, and the sample mean and sample variance are defined as follows. This is the formula for sample mean. So sample mean is equal to the sum of all the observations in the sample divided by n, means average of the sample, and the variance is described by this formula. S square is equal to 1 over n minus 1, and then the sum of all the variances, means this is the x and this is the x bar, which is this one, or the average of the sample. We subtract it from all the observations and divide it with n minus 1, and then from here we can find out standard deviation also. Standard deviation is just the square root of the sample variance. Okay, here x bar, or the sample mean, represents the central tendency, describes the central tendency, while s square, or s square is the variance and s is the standard deviation of the sample. It describes variability of the sample. Okay, so just remember that parameter is related with population and statistic is related with samples. So parameter are the measurements made for population and on population, and statistic are the measurements which are made from the sample. Okay, in the previous slides we have seen what a statistic is. A statistic is actually the measurement that we make on the sample data collected from a population, and population can be following any probability distribution that we have studied before. Now the distribution of that statistic is called as sampling distribution. Okay, means that once we the earlier ones we have seen the probability distributions of populations. Now when we collect sample from that population and we perform some calculations and we get a statistic, then the probability distribution of that statistic is called as, or is referred to as, sampling distribution. Now the process of collecting sample, or the process of choosing sample from the population, is called as sampling. Now we can perform sampling from the population that follow normal distribution, or they have like Poisson distribution or hypergeometric or binomial, or whatever population or whatever distribution they have. So sampling can be performed from any sort of probability, from the population following any sort of probability distribution. So let us consider sampling from a normal distribution. Means that we will select sample from a population that has normal distribution, or that is normally distributed. So let us consider a random sample. This has n number of items in it, which means that it has its sample size is n, and it is collected from a population that had normal distribution, which is represented with this expression. N means normal distribution, and in the bracket these are parameters of this normal distribution. The first one represents mean and the second one represents variance of that population, of that normal distribution. Okay, now if this is the case, that we have collected a random sample of size n from a normal distribution n mu sigma square, then the statistic sample mean, this is sample mean. Okay, the sample mean is a statistic. Then the sample mean will also have a normal distribution. Okay, and that distribution will be expressed with this expression, n mu and sigma square divided by n. So remember that the first parameter is the mean of the distribution, and the second one is the variance. Now both of these are normal distributions, but the difference is that this probability distribution or the normal distribution has a variance sigma square, while this one has sigma square divided by the sample size. Okay, both are normal, but their parameters are different. Now this one can be expressed like this, that the statistic or sample mean has an approximate normal distribution of these parameters. Means sample statistic has approximately normal distribution with these parameters. Means the mean value will be mu, and the variance will be sigma square divided by n, whereas sigma was the variance of the original probability distribution, or the probability or the variance of the population, this one. Okay, now this was the case specifically when the sample is collected from normal distribution, but it also holds true for all other population or all other type of probability distributions. It can be shown like this, that for example we can write this thing. This is if you can recall, this is the expression for standard normal variable. Okay, and in this one, the standard expression is that the first one is the variable minus mu, or the mean of the population, divided by standard deviation of that distribution. Okay, and the standard deviation is very easily calculatable, or we can extract it from here. We can compute it from this value. This is the variance. We take square root of variance and we get standard deviation. Since it was sigma square divided by n, when we take square root of it, it will become sigma divided by square root of n, and square root of n, since it comes in the denominator of a denominator, it goes to numerator. Okay, I hope you understand this expression. Now this one can be expanded in this form. What we did here, we just changed this value. This was sample mean. We have written it like this because mean is equal to sum divided by total, right? So here sum of the sample observations or variables divided by the sample size, it will give us sample mean. So we have just rewritten it in this form, right? So rest of the things are same. Now we can write this like this. Okay, and finally we can write it like this. Now this one, the purpose of showing this was to get this expression. This expression is the sum of the variables xi, right? And if you can recall the central limit theorem, it says that this means irrespective or regardless of whatever the population, the probability distribution of a population is, the sum of the variables which are collected are collected from the data from that population will have an approximate normal distribution. Means that this if this xi is collected from a population, that is any population, can be normal or log normal or any other populations, probability distributions, then means it does not matter from which probability distribution it came from, the sum will always have an approximate normal distribution. And from this expression we can say that this one, the sigma of xi or the sum of xi, has a normal distribution which has mean as n mu and variance as n times sigma square, because this one is written here is the standard deviation, and if we want to compute variance from here, we just square it, so its square will be equal to n sigma square. Okay, then from here we can say that its sample mean will have a normal distribution which is represented like this. So it is the same like this, right? So regardless of the probability distribution of the population, whenever the sample statistic or the sample mean will always follow an approximate normal distribution with these parameters. Okay, now let's move to another one. Okay, now chi-squared distribution. This is a Greek letter chi. It is not read as g, it is read as chi. So chi-squared distribution is another distribution which is the distribution of a statistic extracted or computed from a sample which was selected from a normal distribution. So let us consider that this is the sample of size n which is collected or selected from a normal distribution, represented with this term. Can you guess this notation represents what type of normal distribution? This is a standard normal distribution. A standard normal distribution has mean 0 and variance 1. Then the variable or the statistic, this one, which is computed from these variables, which is actually equal to the sum of the squares of these observations. Okay, So x1 squared plus x2 squared plus x3 squared, so on, plus xn squared. So this variable is equal to the sum of the squares of the observations in this size. This variable then will follow, or the statistic will then follow chi-squared distribution with n degrees of freedom. So this chi-square distribution will have n degrees of freedom, and this n degrees of freedom are the number of items in this sample. So degrees of freedom are actually the maximum number of variables that can independently change values. Okay, so with probability distribution, okay, its probability distribution or probability density function is this one. So normally we do not need to deal with these probability density functions. Mostly we just need to know the method, how to calculate or how to find out the probabilities from probability distributions. Okay, but it is good to know that what the probability density functions are, and it is denoted like this. This is the standard representation of chi-square distribution with n degrees of freedom. So this one, the n subscript represents degrees of freedom, and this is how it is plotted. These are three different chi-square distributions with different values of degrees of freedom. So for n is equal to 5, this is the graph. It is skewed towards left. When there are more degrees of freedom, there are 10, it is more expanded and towards the left side, towards the right side, sorry, and it goes further towards the right side and has wider width. And if we have increased the degrees of freedom to 20 even further, you can see that it is much more wider and expanding towards larger values. Why it is expanding towards larger values? Because as you know that n is the degrees of freedom means that there are more number of items in the sample, and this is the sum. So as more number of items are added, the sum increases, right? So this is expanding towards larger values because the x-axis is showing the value of y, okay, and fy is this one, the probability density function of chi-squared distribution. Now let us see an example of it. This is not a numerical example, but a variable which has a distribution of chi-squared. So for a random sample, this one which is chosen from this distribution is not the standard one. This one has mu and sigma. It can, if the mu is equal to 0 and sigma square is equal to 1, then it will be a standard distribution. But this is a general representation of normal distribution. Just to mention that this sample is chosen from a normal distribution, then this one y is a variable that is expressed with this formula. If you can see it is the top one and the bottom one, both are like the variance. So the variance is actually, it represents the expression of the data, means expansion of the data, not the expression, the expansion or variability of the data. So this one is expressing the variability of the data, or this one we can also write it like this. But how? If you can recall the statistic, the variance statistic that was calculated using this formula. So from here we can rearrange the terms to find the value of this, because if you notice that this one is exactly same as this one, right? So we put that value of n minus 1 times s square divided by sigma square, right? So this one becomes a statistic of this on the numerator. It is the statistic variance or the sample variance divided by the variance of this probability distribution or the population. Okay, so then this one will have a chi-squared distribution with n minus 1 degrees of freedom, and it is represented like this. So this is an example that if we get data, if we collect sample from a normal distribution and it represents means it is expressed, that variable is actually expressed in terms of the variance of the population divided of the sample divided by the variance of the population, like this one. So this is the variance of the sample divided by variance of the population. Then it will follow a chi-square distribution with n-1 degrees of freedom. Okay, now let's move towards another type of distribution of a statistic which is computed from the samples collected from normal distribution. So let us consider a random variable which is expressed as t, okay, which is given like this. Here x is a random variable that has a standard normal distribution. This one has a standard normal distribution, but y has chi-squared distribution with k degrees of freedom. Okay, so x1 has standard normal distribution and y has chi-squared distribution, and this k is the degrees of freedom of the chi-squared distribution that is followed by this variable y. Then this variable t will follow a t distribution which has a probability density function expressed like this. Again, it is not very important for you to memorize this formula because we do not deal it much often. We just need to know that this is how it means, what are the parameters which are included in it. But the important thing to know is how do we calculate, or how do we find out or extract probabilities from these distributions. Okay, that we will do in our examples. And another thing is we should know that how these probability distributions look like. This is how the t distribution looks like. It really strikingly looks similar to a normal distribution, right? So for k is equal to 5, there is one this darker line represents the t distribution with k is equal to 5, where k was actually the degrees of freedom of the chi-squared distribution of y, right? And then k increases to 10, we get this black line, and when k is increased to infinity, it becomes a normal distribution. It exactly becomes the normal distribution. Otherwise it is very close but not exactly the normal. T distribution, we consider a sample which is collected from a normal distribution, this one, and from this sample we have derived two statistics. One is the sample mean and other is the sample variance. Okay, these are computed from this sample. Then this one, x minus mu divided by s over square root of n, which can be expressed like this, and then we can we can see that this part, this one is, if you can recall back, it is the expression of standard normal variable. Okay, it can be written like this. Okay, it is not equal to this, but this is showing that the numerator has a standard normal distribution while the denominator has chi-squared distribution. If you can go back to the previous slide and see, from there you can see that this one was if you can remember, this is the statistic of the sample standard deviation, and this is the sample deviation, this is the standard deviation of the population, right? If you can recall, for chi-squared in the example we saw that s square divided by sigma square, right? But that was a chi-squared distribution, but this is square root of that. Those one s square divided by sigma square, but this is s divided by sigma, so we are taking square root of it times n minus 1. If you can go back to the two slides previous where there was example for chi-square distribution, you can relate this the bottom part or the numerator there, and you will easily you'll have a very clear picture how it comes to this one. Okay, and this one has a normal standard distribution. I hope you understand this one also very well. This is not difficult. Then this thing is, or this variable which is computed from the statistics, computed from these the sample selected from this population, and this variable will have a t distribution with n minus 1 degrees of freedom from here. Now the which is the probability distribution distribution of the statistic, which is collected from the which is computed from the samples collected from a normal distribution. So here the statistic or the variable, random variable, will be f. It is represented with f, and it shows a ratio of, there is a ratio on the numerator, there is a ratio on the denominator also, where w and y are the variables which follow certain probability distributions. W has chi-squared distribution with u degrees of freedom. This is the variable, and it is a random variable, and it has a chi-squared distribution with u degrees of freedom, while y, it is also a chi-squared random variable, and it has its distribution, chi-squared distribution, has nu degrees of freedom. Okay, this is not v, this is nu degrees of freedom. Okay, then both variables are independent from each other, means they do not depend on each other. That dependence means that there are several types of dependencies. Like, for example, we consider that if we select, there is a condition that if we select w, then we cannot select y. It means that y is depending on w. Or if y is appearing, we must select w. This is another type of dependency. Okay, so it is independent of all those, means that we can independently select w and we can independently select y. So both variables are independent from each other under this circumstance and this situation. Then this type of variable, in which the variable is divided by the degrees of freedom of its chi-square distribution in the denominator, is also the same thing. Then this variable y will follow a distribution that is called as f distribution, and it will have k degrees of freedom. Its probability density function is expressed like this. Okay, these gamma functions and the degrees of freedom of chi-square distribution of numerator and denominators both. Okay, and this is how these look, because there are two parameters involved in here. In this distribution, we can see u and v, both will influence its shape. So here u, these three probability distributions of f distribution have same value of u but different values of nu. So nu changes from 5 to 10 to 20, and the shape changes, the height changes, the expansion changes a little bit here at the tail. And if we keep nu constant at 10 and change the values of u, then we can also see the peak shifting towards right, so or the middle of the peak shifting towards the right side. So here, by changing these values, the probability distribution changes its shape also. Okay, so if we have two variables, x1 and x2, in contra means these are the similar like w and y in the previous one. Okay, so now we are calling the samples that we have selected from this probability distribution, as x1 and x2. Here x1 has n1 number of items, and its variance is represented with s1 square, and x2 is selected from this probability distribution, normal probability distribution, which has mu2 as the mean and sigma 2 square as the variance, and this sample has n2 items in it, and its variance is represented with s2 square. Then the variable, this one, or the ratio, this ratio will have an f distribution where n1 minus 1 is the degrees of freedom for the numerator and n2 minus 1 are the degrees of freedom for the bottom one. You can relate this with chi-square distributions also. You go back and see the example of the chi-square distribution. It will make it very clear for you. Okay, so this one is the f distribution having n1 minus 1 and n2 minus 1 degrees of freedom for numerator and denominators.